Alright, so good day everybody. So what we're going to get into today is a little bit of motors. And no, we are not talking about automotive. We are talking about HVAC. So we're going to really get into some of the basic concepts of the motor, what it's made of, how we calculate a couple of different areas of the motor, and we're going to get into at least two of the most basic motors that we use in HVAC. So really what we got to think about is motors really are an important part on any HVAC system. Really what they're doing, if you really kind of want to think about it in like a scientific standpoint, it's really what it's doing. It's taking electrical energy and it's converting it to mechanical energy. We're applying power to it and we're making a motor spin. That motor is now going to be used to drive compressors. It'll be used to circulate hot and cold air across the evaporators, your condenser coils. It'll be used to move air across a warm heat exchanger, combustion chamber if you're dealing with oil. So they're used in a lot of areas in HVAC. We're circulator pumps using to move water in a boiler. So they're there. We have to deal with them on many, many occasions. So most of our motors, they operate off of really like the same principle, but they're really not the same. We have different motors that are out there. We have shaded pole motors, we have split phase motors, we have capacitor start, induction run motors, capacitor start, capacitor run motors, three-phase motors. But the thing is that they all really operate off of the same principle. But their construction and operating characteristics really are what separates them, I guess, from one another. Each one has their own torque. Each one has their own RPMs. So things like that are what really kind of makes things different. So we need to really understand how a motor operates in order for us to effectively troubleshoot. Is we got to really know how it works, how it operates. So the first thing that we need to really remember when it comes to a motor is that they operate off of electricity and magnetism. Now some people might say, well, how is this? How does a motor operate off of magnetism? Well, we're going to get into that. So what we're doing is most of our, pretty much all of our motors really, they have two primary components that are in there. We have a stator and a rotor. So what do they do? So the stator is the stationary portion of the motor. And that portion of the motor is attached to the inside of your motor housing. Okay, sometimes you may refer to the stator as a frame, which is pretty much most common, I think, in my opinion. I mean, I don't think I ever really call it a stator, but that's really what it is. It's the frame of the motor. Okay, the stator is right here. See this bunch of coil wires right here? Okay, that's our stator. Okay, the motor housing is this guy right out here. Okay, this is what houses everything. So what does the stator consist of? The stator consists of your field poles and windings. Okay, field poles are electromagnets. So if anybody has ever messed around with magnets as a child, know that when you have opposite poles, what happens? They attract each other. When you have the same poles, they repel each other, right? So when we apply really electricity to those field windings, I'm generating a magnetic field into those electromagnets. Your motor is also consisted of two types of windings. Okay, you'll have a start winding and a run winding. When you take a motor apart, or even if you ever have an opportunity to, ever take a motor apart and look at the stator itself, you can honestly see your start and your run windings. Usually they are going to be two separate gauge type wires. Okay, usually the start winding is going to be the larger, and then your runs are going to be the opposite. Okay, so what do these things do? Your start winding is really an additional winding in a single phase motor that allows the motor to start when the poles of the stator and rotor are not in the correct position. So the way I always like to think about it, the start winding is what gets the motor to start the actual spinning process. So the start winding has to take a beating to get that motion to go. So the current applied to the start winding is slightly out of phase with that applied to the run winding. And then the run winding of the stator is that allows the motor to actually continue to operate. Okay, so once the start winding gets the motor to spin, the run winding is what actually keeps the motor spinning. Okay, the run winding gets constant voltage until the motor actually shuts off. So when this is all in operation, this is what we kind of see. We have our stator, and we have a rotor. And the rotor is actually what's spinning. So those field windings are the wires that is wrapped around the field poles of the stator. So when power is applied to that field windings, it creates a magnetic field around those field poles. So the rotor is the unit that actually operates as the polarity of that stator's poles change. So when we're dealing with 120 volts of electricity, we know that that's alternating current. So 60 times in 1 second, that polarity in those electromagnets are going to change from positive to negative or north to south. And as we do that, the rotor, which is also made of magnets, oppose and attract each other, and that is what actually makes the motor spin. So the rotor is sometimes called an armature and can be made of coils of wire wrapped around an iron core, or they could be made up of metal bars mounted on an iron core. The rotors that are made out of metal bars and mounted on an iron core, I think, are the most common type rotors that you're going to see. The bars are connected at each end of the rotor to form a complete circuit, and that is called a squirrel cage rotor. So what we're looking at, this is a squirrel cage rotor. So if you look right here, you can see those bars, those metal bars. Those metal bars are what is going to oppose and attract from the stator electromagnets and what makes the rotor actually spin. Okay, so the rotor, when it sits inside the motor, is mounted on the motor shaft that has two bearings, one on each end. So you can see the bearing here, and you can see the bearing here. Okay, so that is also very important to know. Bearings are accurately machined to provide the proper amount of end play for the rotor. Your end bells or end plates close the openings on either end of the motor frame and actually hold the bearings in place. The end bell also supports the rotor when the motor shaft is mounted inside the bearings. So the bearings will actually sit right inside this little housing right here on this side and on this guy. And that is what gives the rotor the support it needs so that it's not grinding up against anything and it has a smooth operating feature. The motor nameplate, which displays all the essential motor information, is mounted on the frame of the motor, as well as your motor terminal box where all of your electrical connections are also mounted. All right. When we are looking at a motor nameplate, this really gives us an idea of what type of motor we're dealing with. It gives us its operating voltage. It's going to tell us our horsepower. It's going to tell us the type of phasing or the number of phases the motor is going to operate at. Obviously, it's going to give us a model number, maybe a serial number. Depending on the manufacturer, it actually might even give you a catalog number for referencing. Sometimes they give you a maximum ambient temperature rating that the motor can actually be in. Sometimes they're rated in Celsius, sometimes they're rated in Fahrenheit. Depends on the manufacturer. It gives you your what type of thermally protected device is in the motor, and it also gives you your manufacturer's type. So a lot of information really can be on a nameplate when we're looking at the motor and trying to figure out what is actually going on with it and what it's actually doing. So the first motor that we want to get into is the shaded pole motor. Now, the shaded pole motor, in my opinion, is probably the simplest of all motors that are out there. There's really not much to these motors. Okay, the shaded pole motor really consists of nothing more than a squirrel cage rotor, an iron core, and two or more rings, or better known as poles, with a coil and a small copper insert. Okay, the insert slows the buildup of the magnetic field just enough to cause rotation towards the magnetic field. Okay, the action provides for induced magnetism into the rotor, and then the rotor will then turn as if it is attracted by the magnetism. A movement of the rotor will continue as long as there is change of polarity of the poles and the rotor. Now, what's really nice about shaded pole motors is that they are actually reversible. You can change the rotation of a shaded pole motor. If we look at this picture right here, you're going to kind of see this little plate here with two little screws. If we take these two little screws or bolts out, this entire piece comes off. And when you take this entire piece out, this rotor will come right out. If I take that rotor out and put the shaft so that it's facing this way, and then reassemble everything, I can actually change the rotation of that shaded pole motor, and the motor will still operate. If the motor happens to stall, or if the bearings freeze, which honestly I don't think I've really seen a shaded pole motor bearings ever freeze, but if they do, the motor windings will usually not burn out. Okay, they're very low torque. There's not a whole heck of a lot of power that's going on with these types of motors. So when the motor is in a locked condition, the windings draw very little current. The direction of the shaded pole motor is always towards the shaded poles. The shaded poles is what this pen is actually pointing to. Okay, shaded pole motors can be made multi-speed by inserting voltage taps into the motor winding. You're not going to make a shaded pole motor a multi-speed motor in the field. You're going to purchase them as as they do come in multi-speeds. You can get them as a single speed or multi-speed. Shaded pole motors are low in cost, but have very low starting torque and very low power factors. Okay, so this is what a shaded pole motor would look like in a wiring diagram. A shaded pole motor only has one winding, and that's going to be the run winding right here. Okay, the run winding, so we got power coming through my winding. I'm going to generate a magnetic field. I'm going to make the guy spin. This is a pictorial of what this guy is actually doing. So here's my L1. It's coming in, wrapping around one pole, coming around, wrapping around another pole, another pole, another pole. And there's those little copper bands that we're talking about. Okay, those copper bands is what helps produce the magnetism and what makes the motor actually spin. The next one that we're going to get into is your split phase motor. These guys are obviously a little bit more beefier. These guys can be used as your indoor blower. They can be used as condenser fan motors. They can be used as many different areas of the field. So your split phase motor is also called an induction start, induction run motor. I don't normally call it that. I'm just going to call it a split phase. Okay? But usually if you want to really sound really smart and stuff like that, yeah, get an induction start, induction run motor. Okay? Sometimes people look at you like you have three heads. These motors use a current relay or a centrifugal switch to remove the start winding from the circuit. Now remember, we're talking about a split phase motor. Shaded pole motor only has one winding in it. That's going to be the run winding. Split phase motors are going to have both. They're going to have the start and the run winding in there. Okay, the start winding works on a phase shift principle. The starting torque and running torque of these guys is relatively low in split phase motors because of that phase shift is so low. Where are we going to find these types? They can be belt driven, usually. They're going to be usually belt driven. Some cases they could be direct drive, but you're going to find them in a lot of your smaller appliances like your washers, your dryers, dishwashers, a lot of your older style furnaces, stuff like that. So this is what your split phase motor will actually look like and how it operates. One thing that we need to understand is that we have a start winding, we have a run winding. Okay, so here's my start winding, here's my run winding. Okay, now remember, these guys are going to have either a current relay or a centrifugal switch on these things. So here, which is commonly sometimes known as your start switch, or better known as your centrifugal switch, which is right here. So what does this guy do? Well, we know that we have a start and a run winding. The centrifugal switch on this particular type of motor removes the start winding from the motor circuit once the motor reaches around 75% of its rated RPMs. Okay, when we're dealing with these types of motors, this is the type of motor that often fails when the motor is started and stopped many times. So what happens is the start or the centrifugal switch is a normally closed switch. So when I am energizing this motor, initially my start and my run winding are energized at the exact same time because we're giving that motor a lot of energy to start. Once that motor starts and that motor reaches around 75% of its rated RPMs, that centrifugal switch is going to open. And when that switch opens, it removes the start winding. It takes it out. It's no longer energized. And once that happens, I'm leaving my run winding, my black here, see this black wire, I'm leaving that energized all the time. which will now leave that motor spinning until I shut it off. Now, why do these things fail? Is because it moves. Remember, it's a normally closed switch, so every time that motor starts, that switch is going to open. Once that motor stops, it's going to close. It's going to keep doing that every single time that motor starts and stops. So eventually, over time, sometimes that switch will fail. And when that happens, I'm going to have my start and run winding either energized all the time, or if the switch happens to be stuck in the open position, the motor is just going to hum. It's not going to spin at all, because the run winding doesn't have enough energy to get the motor to spin. Okay, so there it is right here. Here's my centrifugal switch as it would look like inside a actual motor. Right there. And actually you can also see the set of contacts that will actually open and close based off of the movement of this switch. Another thing that we need to get into is motor speed. Motor speed is determined by the frequency the motor is actually operating at and the number of magnetic field poles on the stator. Okay, motor speed is initially calculated as synchronous speed. Synchronous speed refers to the speed of the rotating magnetic field in the stator. So if a rotor is actually rotating at the same speed as the stator's rotating magnetic field, then the motor is actually running at a synchronous speed, which means both are running at the exact same RPMs. Now, in reality, motors do not run at a synchronous speed. So, in order to figure out what the synchronous speed would be, better known as revolutions per minute, we have to use this following formula. Okay, NS is going to stand for rotations per minute. 120 times frequency divided by the number of poles. So, let's take an example here. We have a motor that we want to calculate its synchronous speed. We have a 2-pole motor and it's operating only at 60 hertz. Now remember, as long as we have at least 2 variables, we can always figure out the third. But in this case, we actually have really 3. So, we're going to plug in those numbers. We have 120 times 60 divided by 2. Remember, we need to know the hertz and we need to know the number of poles. So we plug those numbers in, we get 120 times 30. So if we plug that in, we figure out that the synchronous speed of this particular type of motor is 3,600 RPMs. That is not what motors operate at. Motors have a slip. They have a motor slip on that. When they are running at their full load, they usually will lose a little bit of their RPMs, and that is called a slip or a motor slip. And that's usually somewhere around maybe 4 to maybe 5% of that synchronous speed that we just calculated. Okay. Now, why do we have a motor slip? Well, it's because of, motor design, friction being generated as the rotor is spinning inside the stator, your construction of your windings that are in there. So there's a couple of different factors that actually cause a motor to actually have a motor slip. Most motors usually are, I probably want to say maybe about 95% efficient, especially your bigger motors. Your smaller motors, it depends. They could be maybe about 40 to maybe 50% efficient. Again, I really don't want to be quoted on that, but it does depend on the construction and the friction rate and all that stuff on motors that really kind of determine motor slip. There is a formula that you can use to calculate the motor slip, but off the top of my head, I don't remember what it is. Okay, but other than that, calculating motor horsepower is another thing that we can do sometimes to figure out what what the motor is actually using to operate. Horsepower is rated by the power consumed by the motor. The power consumed is rated in watts, and we need to remember that 746 watts of power is equal to 1 horsepower. So a 5 horsepower motor will consume roughly around 3,730 watts of electricity, assuming that that motor is actually at 100% efficient. Now, again, taking into effect motor slip, friction rate, and all that stuff, we know that a motor is not going to be operating at exactly that amount of wattage. So we have to sometimes calculate stuff to see whether or not a motor is operating within the correct ranges that it's actually rated for. So when the wattage and voltages are known, Ohm's law makes it possible to determine the amount of amperage draw at your full load conditions. So locked rotor amps is a common term that you're going to hear when you're dealing with motors, or better known as LRA. Okay? When we deal with locked rotor amps, it's at startup and before the motor begins to turn. The current flow is determined by the resistance of the windings. Starting current is about 6 times higher than the normal running amperage. Because remember, we're taking an object that is at rest and not moving, and now applying electrical energy to get that motor to spin. So when it does this, we are going to have a large amount of amperage at first once that motor starts. You can see your lock rotor amps if you put your amp meter on your wires and then turn the motor on. Once that motor starts, for a very brief second, you can actually see what the lock rotor amperage is for that particular motor. Another term that we have to deal with is what we call full load amps, or FLA. Okay, full load amps refers to the amperage the motor draws when it is at normal speed and fully loaded and working at its 100% peak. Okay, most induction motors operate at less than full load amps because the motor is rarely working at full load conditions. So when you're looking at a nameplate on a motor, you may see LRA rating and an FLA rating. When we are troubleshooting a motor and we're taking amperages, we want to make sure that the motor is operating at less than the full load amps. If it is operating at a higher FLA than what it's rated for, there's probably a chance that the windings inside the motor are starting to break down, and eventually the motor is going to fail. Okay, it's something that you may want to just maybe note on a service slip, or maybe let the homeowner know that it is running a little high on its amperage. It may fail, and maybe in another year or so. But just let some people know that they do have a problem with the motor. If everything is within range or operating below what the motor is rated for, then I would probably say that the motor is still in relatively good condition and you probably shouldn't have much of a problem with it. Motors will come in with overload protectors. Usually they are a thermal overload protector. And these things are found in usually a bimetal disc that is actually inside the motor itself. and is used to open the circuit if the motor happens to overheat for whatever reason. So that's just another thing that we have to take into account when we're troubleshooting a motor. If the motor is really, really warm to the touch or hot, chances are the thermal overload inside the motor has taken the motor out, and it's not going to work until the motor is cooled off. Or in some cases, the bimetal disc just does not reset itself and the motor needs to be replaced.